Tonight, we're chasing one of the strangest truths in all of physics. What if two particles separated by galaxies can still know what the other is doing instantly? Einstein called it spooky action at a distance. But it's not science fiction. It's been proven over and over again. From quantum computers to teleportation, from unbreakable encryption to the very fabric of space and time, this strange force, called quantum entanglement, might hold the key to how reality actually works. In this documentary, we'll follow the trail from Einstein's defiance to modern-day experiments stretching across continents and into orbit. We'll explore how something so invisible, so impossible is now being used to reshape the future. But the deeper we go, the stranger it gets. What if entanglement isn't just real, but the foundation of everything? Stay with me, because what you're about to see might change how you understand the universe forever. So how do we begin to make sense of this thing called quantum entanglement? It sounds like science fiction. It behaves like magic. And yet, it's arguably the most rigorously tested and mathematically confirmed feature of the quantum world. But to understand what it really is, and why it might just be the most important clue to the nature of reality, we first have to untangle some misconceptions. Imagine two particles. Let's say they were born from the same parent particle in a high-energy event, maybe deep inside a lab's particle collider, or in the early moments after the Big Bang. These two particles now fly apart, perhaps traveling millions of kilometers from one another, and yet something extraordinary happens. Measure the state of one particle, its spin, its polarization, its energy, and the other instantly responds, as if it knew what just happened, even if it's on the other side of the galaxy. No message passed between them, no delay, no classical signal, just a perfect, eerie correlation that defies all common sense. That's quantum entanglement. But it's not just a quirky glitch in nature, it's a feature, a central one that Albert Einstein despised, one that Niels Bohr defended, and one that has since been observed in labs and satellites using photons, atoms, and even large molecules. It violates our most sacred intuitions about the universe, that space separates things, that cause must precede effect, and that information can't travel faster than light. To grasp how revolutionary this is, we have to revisit what quantum physics actually says. In the classical world, a particle is a tiny object with fixed properties. It has a specific position, a defined velocity, and a measurable energy. But in the quantum world, things don't exist in fixed states until they are measured. Before observation, a particle isn't here or there. It's described by a wave function that spreads across many possibilities. Measurement collapses that wave function into a definite outcome. It's like flipping a coin that exists in a swirling cloud of both heads and tails until your eyes land on it, and then suddenly it's one or the other. Now here's where it gets wild. When two particles are entangled, their wave functions are no longer independent. Instead, they form a single unified wave function that describes the system as a whole. This means you can't describe one particle's state without referencing the other, even if they're separated by light years. In this way, entangled particles behave not like two distinct objects, but like one connected entity, smeared across space. For example, if you measure the spin of one electron and find it's pointing up, the spin of its entangled partner will always point down. Not because one caused the other, but because both outcomes were always part of a shared quantum state. The universe doesn't decide which spin is up and which is down until one is measured, but once that choice is made, the other is instantly locked in. Einstein hated this idea. To him, it suggested either faster-than-light communication, or worse, that the particle's properties didn't really exist until they were measured, a concept he dismissed as absurd. He famously derided entanglement as spooky action at a distance. In 1935, he, Boris Podolsky, and Nathan Rosen published a paper, now known as the EPR paradox, arguing that quantum mechanics must be incomplete. They proposed that some hidden variables were at play, variables that determined the outcome of measurements but were simply unknown to us. If such variables existed, they reasoned, the world would still be local and deterministic. There would be no need for spooky correlations. But the quantum community, led by Niels Bohr, pushed back. Bohr argued that Einstein had misunderstood the nature of quantum reality. The theory wasn't incomplete. It was just fundamentally different from classical expectations. According to Bohr, asking about the properties of a particle before measurement was like asking the color of a sound. It simply didn't make sense in quantum terms. Reality, in this view, wasn't something that existed independent of observation. It was shaped by observation. For decades, this debate simmered. The mathematics of quantum mechanics worked beautifully. It could predict particle behavior with extraordinary precision. But the philosophical implications remained murky. Was entanglement a strange trick of incomplete knowledge? Or was it a real physical phenomenon that forced us to rethink everything we knew about space, time, and causality? Then came a breakthrough. In 1964, the physicist John Bell published a theorem that would change everything. Bell devised a mathematical inequality that could be tested in the lab. If hidden variables were responsible for quantum correlations, as Einstein had hoped, then the results of entanglement experiments would obey Bell's inequality. But if quantum mechanics was right, and entanglement was a genuine non-local effect, the inequality would be violated. This set the stage for a new era of physics, one where Einstein's spooky action could finally be put to the test, and the results, as we'll explore, would leave no room for doubt. But before we reach the experiments that shook the foundations of reality, it's worth pausing for a moment to reflect on what's really at stake here. Because this isn't just about subatomic particles or mathematical equations. This is about the very structure of reality itself. If entanglement is real, and the evidence suggests that it is, then the universe is far more connected, far more holistic, and far stranger than we ever imagined. You are not made of isolated classical particles. You are composed of quantum systems, nested within quantum systems. And if those systems can remain entangled across time, across space, then perhaps nothing in the universe is ever truly separate. Perhaps we're all woven together by invisible threads of information stretching through the cosmos, linking cause and effect in ways we're only just beginning to understand. So what does that mean? For physics? For the future of technology? For our place in the universe? That's the mystery at the heart of this journey. And as we step into the next chapter, we'll follow the story of how the world's greatest minds set out to put that mystery to the test and discovered something that even Einstein couldn't explain. To fully grasp the strangeness of quantum entanglement, we must go back nearly a century, to a time when the foundations of physics were undergoing a seismic shift. The classical world, the one Isaac Newton gave us, had reigned supreme for centuries. Deterministic, logical, and built on cause and effect. A world where, if you knew the position and momentum of every particle, you could, in theory, predict the entire future of the universe. But in the early 20th century, a new kind of physics began to emerge, one that was probabilistic, uncertain, and utterly bizarre. This was the era of quantum mechanics. Born out of necessity to explain strange results in atomic physics, it was a theory that treated particles not as discrete, billiard ball objects, but as wave functions, mathematical entities that encoded the probabilities of all possible outcomes. Measurement, in this view, didn't just reveal a pre-existing property, it created it. The act of observing forced the system to choose a state. Albert Einstein, one of the architects of modern physics, was deeply unsettled by this. He had already upended the scientific world with his theories of relativity, but the probabilistic nature of quantum mechanics left him cold. God does not play dice, he famously remarked, expressing his discomfort with the idea that randomness, not certainty, governed the universe. In 1931, Einstein began developing thought experiments to probe the limits of this new theory. He wanted to demonstrate that quantum mechanics was incomplete, that there must be some deeper hidden reality beneath the surface. These ideas culminated in a collaboration with two younger physicists, Boris Podolsky and Nathan Rosen. In 1935, the trio published what became one of the most important and controversial papers in the history of physics. Can quantum mechanical description of physical reality be considered complete? This paper, now known as the EPR paradox, introduced a simple but powerful argument. Suppose you have two particles that interact and then move far apart. According to quantum mechanics, their properties are now entangled, their states are correlated. If you measure one particle's position, the other's position becomes known instantly. Likewise, if you measure its momentum, you instantly know the other's momentum. But Heisenberg's uncertainty principle says you can't simultaneously know both the position and momentum of a single particle with perfect accuracy. So here's the catch. If the first measurement instantly determines the second particle's property, then that second property must have already existed, regardless of whether it was measured. Otherwise, how could the universe know what to reveal? To Einstein, this meant that quantum mechanics was missing something, hidden variables that encoded these properties beneath the surface. The wave function, in this view, was merely a statistical tool, not a complete description of reality. Niels Bohr, Einstein's longtime philosophical rival, wasn't having it. His rebuttal, published shortly after the EPR paper, was as enigmatic as quantum theory itself. Bohr argued that the EPR team had misunderstood the nature of measurement, context, and quantum states. To Bohr, the idea of an independent reality, a property that existed without being measured, was meaningless. Quantum systems were not incomplete, he insisted. They were inherently non-local. Measurement did not reveal reality, it participated in it. Enter Erwin Schrödinger, another quantum pioneer. In the same year as the EPR paper, Schrödinger wrote a now famous letter in which he introduced the term Verschränkung, or entanglement. He recognized that this strange linkage between particles wasn't a side effect of quantum mechanics. It was at the very heart of it. I would not call entanglement one, but rather the characteristic trait of quantum mechanics, he wrote. Schrödinger's insights went further. He realized that entanglement could occur not just with simple properties like spin or momentum, but across complex systems. He envisioned a world where entire systems, molecules, atoms, perhaps even living things, could become entangled in ways that defied ordinary understanding. This is where he introduced another famous thought experiment, the cat in a box. In Schrödinger's mind, quantum mechanics didn't just apply to particles in labs. It extended to the macroscopic world. His cat, both alive and dead until observed, was meant as a criticism, a way to expose the absurdity of applying quantum rules to everyday objects. But ironically, the cat became an icon of quantum weirdness, and the deeper lesson was clear: the boundaries between quantum and classical weren't as sharp as we once thought. So, by the mid-1930s, quantum theory had split into two philosophical camps. On one side, Einstein, seeking a deeper, more complete reality, something objective and local that restored sanity to the universe. On the other, Bohr and Schrödinger, embracing the strange, probabilistic world of entanglement and uncertainty. The debate raged on, but for decades it remained purely philosophical. There was no experiment that could decide the question definitively, no physical test that could confirm whether quantum entanglement was real or just a mathematical trick. But then came John Bell. A quiet, brilliant physicist working at CERN, Bell wasn't satisfied with the status quo. In 1964, he crafted a brilliant mathematical argument that reframed the debate. He showed that if hidden variables existed, if Einstein was right, then the results of certain experiments would obey strict statistical limits. But if quantum mechanics was correct and entanglement was real, those limits would be violated. Bell had turned a philosophical question into a testable proposition. Suddenly, the question of whether entanglement was even real wasn't just academic, it could be measured. And so, nearly 30 years after the EPR paper, the race was on. Physicists began designing experiments to test Bell's inequalities, to determine once and for all whether our universe was bound by classical rules or whether it was truly entangled. The implications were staggering. If Bell's inequalities were violated, it would mean that reality is not local. That information, or correlations, can travel faster than light. That the world we perceive, divided by distance and time, is in fact bound together in invisible ways. Einstein's worst fears would be confirmed, and yet it would also mean that Bohr, Schrödinger, and the strange machinery of quantum theory had been right all along. But as with everything in quantum physics, nothing comes easily. The experiments would be delicate, complex, and fraught with loopholes. Measuring entanglement is like chasing shadows. Every test must rule out alternative explanations. Every result must hold up under scrutiny. Still, the world's physicists were ready. They had the theory, they had the challenge. And as we'll see in the next chapter, they had the will to find out whether reality itself, at its most fundamental level, obeys the rules of classical logic or dances to a quantum rhythm. For decades after Einstein and Bohr locked horns over the nature of entanglement, the argument remained suspended in a kind of theoretical purgatory. The math worked, the predictions held, but the universe had not yet rendered its verdict. That changed in the second half of the 20th century, when physicists set out to do what had once seemed impossible, test the very fabric of reality in the laboratory. The story begins, perhaps surprisingly, not with high-tech quantum computers or orbital satellites, but with a pair of polarized photons and a beam splitter. In 1949, Chinese-American physicist Chen-Xiong Wu and her collaborator Irving Shaknoff conducted one of the earliest experiments to observe quantum correlations between entangled photons. They weren't testing Bell's inequalities; those wouldn't exist for another 15 years, but they had already begun to see the strange statistical fingerprints of quantum entanglement. Their work quietly laid the foundation for what would become one of the most ambitious scientific quests in history. Fast forward to 1972. Physicists Stuart Friedman and John Clauser designed the first experiment explicitly aimed at testing Bell's theorem. Using calcium atoms to emit entangled photons, they measured correlations in photon polarization at different angles and compared the results against the bounds set by Bell's inequality. If Einstein was right, those correlations would stay within a certain classical limit. If quantum mechanics held, they would break it. And break it they did. Their data showed clear violations of Bell's inequality, suggesting that entanglement was not just a theoretical artifact, it was real. But there were problems. The experiment had loopholes, potential cracks through which classical explanations could still crawl. One of the biggest was the detection loophole. Not all photons were detected, and the ones that were might not have been a fair representation of the whole. Another was the locality loophole. The measurement settings on one detector might have, in theory, influenced the other due to some unknown signal. While unlikely, these gaps left just enough room for skeptics to say, "Not so fast." Then came the man who would electrify the field, Alain Aspect. In the early 1980s, at the Institut d'Optique in France, Aspect and his team performed a series of increasingly sophisticated experiments designed to close those loopholes. They improved detector efficiency. They randomized detector settings during flight, ensuring no hidden communication could coordinate the outcomes. And once again, the results were unambiguous. Bell's inequality was violated. Entanglement, it seemed, was not only real, it was unavoidable. Still, the loopholes didn't die easily. Physicists are nothing if not thorough, and entanglement makes extraordinary claims. And as the saying goes, extraordinary claims require extraordinary evidence. That evidence arrived in force in the 21st century. In 2015, 3 independent groups located in the Netherlands, Austria, and the United States simultaneously achieved what had long been considered the gold standard, loophole-free Bell tests. These experiments closed both the detection and locality loopholes with unprecedented rigor. At Delft University, entangled electrons in diamond were measured with settings chosen in real time by random number generators. The measurement stations were placed far enough apart that light itself couldn't have traveled between them in time to coordinate a response. The outcome? Quantum mechanics triumphed again. Bell's inequalities were shattered, definitively. The local hidden variable theories that Einstein had hoped for were finally ruled out. The universe, it turns out, really does allow for non-local connections. Measurement outcomes on one side of an experiment could not be explained by any local influence. Entanglement was now not only a theoretical curiosity or a mathematical convenience, it was a demonstrable fact of nature. And it wasn't just happening in arcane laboratory conditions. It was reproducible, reliable, and universal. But nature wasn't done surprising us. In 2017, scientists at the Chinese Academy of Sciences used a satellite called Metis to entangle photons and transmit them across 1,203 kilometers, far beyond anything previously achieved. This quantum link crossed cities, mountains, and the vacuum of space, maintaining its integrity despite atmospheric distortion and enormous physical separation. This wasn't just a test of Bell's theorem. It was a demonstration of quantum communication at scale, and it opened the door to a new kind of technology, a world where quantum signals might one day travel around the globe, immune to eavesdropping, perfectly synchronized, and profoundly secure. Then in 2020, researchers pushed entanglement into even stranger territory. Until then, most entangled systems involved tiny particles, photons, electrons, single atoms. But what about objects on a larger scale? Could something visible to the naked eye still be entangled? In a groundbreaking experiment, scientists created entanglement between macroscopic systems, oscillating mirrors, vibrating crystals, even clouds of atoms acting in concert. These weren't just microscopic events. These were physical systems that you could almost call tangible. The barrier between the quantum world and the classical world began to blur. And if entanglement could stretch into the macroscopic, it begged the question, is the classical world just an illusion? Are we living in a decohered tangle of quantum information barely holding itself together? Then, just a few years later in 2023, something once unthinkable happened. Entanglement was observed between top quarks at the Large Hadron Collider. These aren't low-energy, stable particles like electrons. Top quarks are heavy, unstable, and decay almost instantly, and yet even in that vanishing flash of existence, they managed to remain entangled. It was the highest energy demonstration of quantum entanglement ever recorded, and it confirmed that entanglement is not a laboratory oddity. It's a feature of reality itself, at all scales, in all corners. It's hard to overstate what this means. When the EPR paper was written in 1935, there were no satellites, no superconducting circuits, no ultra-fast random number generators. Einstein couldn't have imagined entangling particles in orbit. But today, we've not only confirmed that entanglement is real, we've begun to use it in technology, in information, and perhaps soon, in how we view the architecture of the universe itself. And still, the questions grow deeper. If particles can remain connected beyond space and time, what else might be entangled? Can space-time itself be entangled? Are black holes governed by the same hidden connections? Could entanglement be not just a side effect of quantum theory, but the very foundation of reality? As we look ahead to where this strange journey leads, we turn next to the cutting edge of quantum research in 2025, where entanglement is being bent, shaped, visualized, and engineered in ways even Einstein might have called miraculous. It's easy to think of entanglement as an abstract curiosity, a feature of physics so subtle and specialized that it belongs only in laboratories and chalkboard equations. But the truth is, we are now entering an era where entanglement is no longer just observed. It's being engineered, controlled, directed. In 2025, this phenomenon, once dismissed as spooky, became a tool, and one with capabilities that stretch the imagination. The first revelation of the year came from an unexpected place: gravity. For decades, physicists have tried to bridge the gap between quantum mechanics and general relativity. Two theories that, while immensely successful in their own domains, have never fully agreed on the nature of the universe. But this year, a team of researchers at the Max Planck Institute took a bold step toward unification by exploring the connection between entanglement and the curvature of space-time itself. Using entangled particles placed near massive rotating bodies, precisely controlled systems simulating gravitational wells, they discovered measurable shifts in entanglement fidelity depending on the local curvature of space. In simpler terms, the strength and behavior of entanglement was subtly influenced by the geometry of the space it traveled through. While this doesn't prove that gravity is caused by entanglement, it adds serious weight to a provocative idea that space-time itself may emerge from quantum entanglement at a deeper level. The thought that space and time might not be fundamental but born from hidden correlations between quantum systems is more than theoretical poetry. It's a shift in what we think the universe is. Meanwhile, at MIT, another team unveiled something that feels like science fiction made real: entanglement microscopy. For the first time, scientists created a method to visualize entanglement at the microscopic scale, not just infer it through statistics or detector clicks, but see the imprint of entanglement between particles in real time. The technique involves quantum light sources paired with weak measurements, revealing subtle interference effects that occur only when systems are entangled. The images themselves are strange, ghostly fields that shimmer with non-local structure, but they offer a new way to probe the invisible. It's as if we've finally built a telescope for the quantum world, and we're seeing entanglement not as a calculation, but as a pattern etched into reality. But 2025 didn't just deliver breakthroughs in how we observe entanglement, it showed us new ways to create it. One of the most fascinating developments involves something called total angular momentum entanglement. Traditional entanglement often links basic properties like spin or polarization. But this new research, published in Nature Quantum Technology, used laser-cooled atoms to entangle their total angular momentum states, an intricate combination of spin, orbital, and internal motion. Why does this matter? Because these multidimensional entangled states could become the foundation for future quantum processors, where each particle can encode vastly more information than ever before. It's like upgrading from Morse code to a full symphony within a single atom. And then there was the surprise no one saw coming: entanglement applied to strategy. In a collaboration between game theorists and quantum physicists at Oxford and the University of Tokyo, researchers demonstrated that entanglement can confer measurable advantages in competitive decision-making scenarios. In their quantum version of the classic prisoner's dilemma, entangled agents were able to achieve cooperative outcomes that outperformed all classical strategies. This isn't just theoretical musing. The experiment used real entangled qubits and tracked how information could be shared or withheld across quantum systems playing against each other. The result? A new frontier called quantum game theory, where entanglement changes the very structure of choice and consequence. It's a glimpse into a future where economic models, negotiations, even artificial intelligence could evolve in ways that are no longer purely classical. But perhaps the most striking experiment of the year came out of a small but tenacious lab in Switzerland, where scientists managed to entangle individual molecules, not atoms, not photons, but entire molecules. Using finely tuned magnetic fields and custom-designed optical traps, they brought two complex organic molecules into entanglement and confirmed the result via correlated spectroscopic signals. Molecules, with their tangled clouds of electrons and nuclei, represent the next level of scale in quantum control. This isn't just a proof of concept, it's the first step toward molecular-scale quantum devices, new kinds of sensors, switches, and processors built not from artificial chips, but from the building blocks of matter itself. Across all of these developments, one theme stands out. We are no longer at the mercy of entanglement. We are beginning to wield it. Not fully, it's still a wild and temperamental force, but enough to make real things happen. Enough to build machines, send messages, test theories, and push the boundaries of what information, locality, and connection even mean. This moment in history is not unlike the early days of electricity. At first it was invisible, mysterious, even terrifying. Then it was a novelty. Then a tool, and now we cannot imagine life without it. Entanglement may follow the same trajectory. What was once a ghost in the machine may soon become the machine itself. Of course, these discoveries raise as many questions as they answer. If entanglement can reach across space and now scale, if it can be measured, manipulated, and trusted to encode information, then what else might it be capable of? Could we one day entangle biological systems, neurons, proteins, perhaps even living cells? Could our own consciousness be connected through hidden quantum threads, as some fringe theories suggest? Those answers are still far beyond our reach. But 2025 has made one thing absolutely clear. Entanglement is no longer a philosophical oddity. It is a scientific tool, an engineering principle, a physical force to be mapped, harnessed, and ultimately understood. And as we turn from research to application, we now enter the realm of quantum technology, where entanglement isn't just a phenomenon to admire, but the engine behind a revolution that's already begun. If the 20th century belonged to the digital revolution, the 21st may be remembered for something deeper, stranger, and infinitely more powerful. Because at the heart of the quantum age, beneath the buzzwords and billion-dollar investments, is a phenomenon that defies everything we thought we knew about computing: quantum entanglement. To understand how entanglement fuels this next wave of innovation, we have to first break our addiction to classical logic. Traditional computers, your phone, your laptop, even supercomputers, operate on bits. These bits are binary, 1 or 0, on or off. They follow predictable rules and precise logic gates. Even the most powerful machines on Earth are built on this rigid foundation, a chain of binary decisions, one after another. Quantum computers are different. They don't run on bits. They run on qubits, quantum bits, which can exist in multiple states simultaneously thanks to a principle called superposition. But it's entanglement that gives qubits their true power. Because when qubits are entangled, their states become linked, so deeply in fact, that the state of one instantly affects the state of another, no matter the distance between them. The result is a kind of computational parallelism that classical systems simply cannot match. Picture it like this. A classical computer trying to solve a complex problem is like trying to find one specific page in an endless library by flipping through books one at a time. A quantum computer, powered by entanglement, is like reading all the pages at once, not through speed, but through structure, a structural web of probability, correlation, and connection. Take Shor's algorithm, for example, a quantum procedure that can factor large numbers exponentially faster than any known classical algorithm. This matters because factoring underpins the encryption that protects everything from bank accounts to military secrets. Without entanglement, Shor's algorithm wouldn't work. It's the entangled qubits that allow the system to coordinate across countless possible paths simultaneously, arriving at solutions in ways classical logic can't emulate. Then there's Grover's algorithm, which can search unsorted data far more efficiently than any traditional method. Again, entanglement plays the crucial role. It allows qubits to be entangled across all possible states in a way that amplifies the probability of correct answers and suppresses wrong ones. It's not brute force, it's a kind of quantum resonance. But we're not talking about science fiction anymore. Companies like IBM, Google, and D-Wave are building quantum processors right now. In 2019, Google claimed quantum supremacy, the point where a quantum processor performed a task that no classical computer could replicate in a reasonable time frame. That processor relied heavily on entanglement between dozens of superconducting qubits cooled near absolute zero. Still, we're in the early days. Quantum computers are finicky, sensitive to the slightest disturbances from the environment. This is where entanglement cuts both ways. While it's a superpower for computation, it's also fragile. Maintaining entanglement across a large number of qubits and keeping it coherent long enough to compute is one of the greatest engineering challenges of our time. That's why error correction has become one of the hottest frontiers in quantum research. Classical computers can copy bits and compare them for errors, but quantum information can't be copied directly. That's forbidden by the no-cloning theorem. So instead, researchers use entangled states across multiple qubits to detect and correct quantum errors without measuring or destroying the information itself. It's like defusing a bomb without opening the case, using correlations to infer what's gone wrong and fix it, all while preserving the quantum system. The potential rewards are staggering. Quantum computers could revolutionize materials science, simulating molecular interactions too complex for any classical machine. They could reshape drug discovery, optimize logistics on global scales, and crack codes previously thought unbreakable. And underpinning all of it, quietly but critically, is entanglement, the invisible scaffolding that holds the quantum processor together. But entanglement's power isn't limited to computation. In quantum cryptography, it offers a new kind of security, one that doesn't just make eavesdropping difficult, but physically impossible. Consider quantum key distribution, or QKD. In a typical protocol like BB84 or ECRT scheme, two parties, Alice and Bob, share a stream of entangled photons. Because of the laws of quantum mechanics, any attempt to intercept or measure these photons by a third party, Eve, will disturb the system in a detectable way. Unlike classical encryption, which relies on mathematical complexity, QKD relies on physics itself. If someone tries to listen in, the entanglement collapses and the intrusion is revealed instantly. This kind of communication is already being tested. In 2020, China's Michius satellite used entangled photons to perform the world's first quantum encrypted video call across continents. The signal traveled from space to ground stations thousands of kilometers apart, secure, unhackable, and protected by the very fabric of quantum theory. But there's more. Entanglement also enables quantum teleportation, the ability to transfer the state of a quantum particle from one location to another without physically moving the particle itself. It sounds like science fiction, but it's been demonstrated repeatedly in labs across the world. Here's how it works. Two parties share an entangled pair. A third particle, say one you want to teleport, is introduced and entangled with one half of the pair. Then, through a specific measurement called a Bell state analysis, the state of the third particle is transferred to the distant particle, instantly and without crossing space. No information moves faster than light, but the effect is real. The particle's state disappears here and reappears there. Teleportation doesn't transport matter, it moves information. But in the quantum world, that's everything. It's already being used in early-stage quantum networks where nodes of entangled qubits could one day span entire cities or even nations, forming the backbone of a quantum internet. And then there's superdense coding, a lesser-known but equally powerful effect. With entanglement, it's possible to transmit two classical bits of information by sending just one qubit. By manipulating the shared entangled state, a sender can encode additional data that the receiver can decode using their half of the entangled pair. This form of quantum communication could one day radically improve bandwidth and signal integrity in future networks. All of this, computation, cryptography, teleportation, compression, it all flows from the same core phenomenon. Entanglement isn't a single-use anomaly. It's a multi-purpose engine, a kind of quantum Swiss Army knife that allows us to manipulate, encode, and protect information in ways that were impossible just decades ago. But we're still scratching the surface. The tools are primitive. The systems are noisy. The distances, though growing, are still short. Yet every milestone brings us closer to a new kind of reality. One where information flows not through wires or satellites, but through entangled fields, probabilistic echoes, and non-local links. Where machines no longer think in binary but in wave functions. And where secrets, once whispered across fiber optics, are now protected by the laws of the cosmos. In the next leg of our journey, we'll explore how entanglement is transforming how we see the universe, through measurements more precise, images more detailed, and sensors more sensitive than anything we've ever known. The quantum eye is opening. There was a time when measurement was limited by the size of our tools. We gauged distances with rulers, mass with weights, and light with prisms. But the 21st century doesn't measure the world with objects, it measures with correlations, and the most powerful correlations we've ever discovered are quantum entanglements. They don't just refine our instruments, they redefine what it means to observe. Enter quantum metrology, a field where entanglement is leveraged, not as a curiosity but as a functional resource. In classical physics, precision is limited by the so-called shot noise limit, essentially the randomness that arises from counting discrete particles like photons. Send 1 million photons into a detector and you'll get a statistical spread in your result. The more photons, the better the signal-to-noise ratio, but there's a ceiling. That ceiling is dictated by classical statistics. Quantum entanglement changes the game. By using entangled particles instead of independent ones, physicists can reach what's called the Heisenberg limit, where the precision improves not with the square root of n, but directly with n, the number of particles. That's an exponential leap in sensitivity. Instead of more power, we get more clarity. Instead of blasting the system with brute force, we extract more signal from the same amount of light. Consider gravitational wave detectors like LIGO. These machines are already among the most sensitive instruments ever built, capable of detecting ripples in space-time from colliding black holes over 1 billion light-years away. But to push further, into weaker, more distant signals, researchers are now turning to entangled photons. By squeezing the light into quantum states with entanglement-enhanced correlations, they reduce the uncertainty in phase measurements, effectively tuning the instrument to listen beyond classical limits. In 2025, a new system called Q-Vista was unveiled by a European collaboration, an entanglement-enhanced interferometer that demonstrated a 10-fold improvement in resolution over conventional designs. Instead of just detecting gravitational waves, it could map minute changes in local space-time curvature, potentially allowing scientists to detect subtle anomalies, tiny echoes of cosmic events or shifts in the Earth's gravitational field caused by underground structures or tectonic motion. It wasn't just a better tool, it was a new kind of vision. This concept has been extended to quantum imaging, where entangled photons are used to create images that defy classical constraints. One striking method is called ghost imaging, where an image is reconstructed using entangled photon pairs, even though the detector that records the image never directly interacts with the object being imaged. It sounds impossible, yet it works. One photon illuminates the object, but is never seen. Its entangled partner goes to a detector, and because the two photons share correlated histories, the detector can reconstruct the image based on information it never directly received. In the lab, ghost imaging has produced pictures of objects in low-light conditions where classical imaging would fail. But the implications go much further. This technique has already been proposed for use in biomedical imaging, scanning tissue without radiation or even visible light. It's also being considered for deep space astronomy, where detectors might one day image planets or stars obscured by dust clouds or gravitational lensing, using entangled photon streams that pierce through interference like nothing else can. And then there are the sensors, devices that measure not pictures but fields, magnetic fields, electric fields, temperature gradients, even time itself. Entangled particles can act like needles suspended in quantum uncertainty, exquisitely sensitive to the slightest disturbance. At MIT's Lincoln Lab, entangled atomic sensors have been used to measure changes in magnetic fields at scales of just a few femtoteslas. That's 1,000,000 times smaller than the magnetic field of Earth. One 2025 project out of Switzerland used an array of entangled ions to detect changes in gravitational potential as a person simply walked past the lab. Not their footsteps, not their sound waves, just their mass, warping space-time by a fraction of a billionth. The detector was so sensitive that it could, in principle, detect a mouse running across a floor above it, not through vibration, but through gravity itself. It was, in effect, a gravitational motion detector, built not from gears, but from entanglement. Quantum entanglement also underpins atomic clocks, the most precise timekeeping devices ever created. These clocks don't tick with gears, but with the vibrations of electrons in atoms, measured using lasers and quantum transitions. Entangled atomic clocks have demonstrated levels of precision so high they could detect the difference in time between your head and your feet, just from the curvature of Earth's gravitational field. In the near future, these clocks may be used to map Earth's gravity in real time, aiding geophysics, navigation, and even climate science. And in space, entangled sensors could monitor cosmic background radiation, detect tiny irregularities in dark matter fields, or serve as the backbone of navigation systems far more accurate than GPS. In fact, China's quantum satellite projects are already testing entangled signal transmission for space-based quantum sensing networks. The goal, to build a constellation of detectors so precise they could detect not just where you are, but how space-time itself is shifting around you. None of this is theoretical. It's happening now. Quietly in labs and clean rooms around the world, entanglement is becoming the lens through which we see. Not in metaphors, not in analogy, but in photons, particles, and atoms, entangled systems acting like extensions of our own senses. We no longer measure reality by touch, light, or resistance. We measure it by correlation, by the invisible handshake between quantum systems that lets us peek behind the curtain of what is. Entanglement isn't just about particles being weird. It's about us learning to use that weirdness to our advantage. But as we build our machines, something else stirs in the shadows of entanglement. Not just technology, but meaning. Because the more we test this invisible bond between distant particles, the more we must confront its philosophical weight. If measuring one particle affects another instantly, without signal, without force, then what does that say about the nature of reality itself? In the next chapter, we step into the world of quantum philosophy, where scientists and thinkers have wrestled with this very question. Entanglement isn't just a tool, it's a crack in the foundation of how we understand truth, time, and even free will. There are moments in science where discovery doesn't just expand what we know, it changes what we believe. Quantum entanglement is one of those discoveries. It's not just a physical mechanism or a technological breakthrough, it's a philosophical earthquake, the kind that shakes the bedrock assumptions we once held as unshakable. Because if entanglement is real, and by now every major experiment says it is, then something is deeply wrong with our classical view of reality. The idea that objects have properties independent of observation, that events are local, that causes precede effects. All of it begins to crumble under the weight of entanglement's strange implications. Start with the issue of non-locality. In everyday life, if two things are far apart, they can't influence each other instantly. Signals are limited by the speed of light. But entangled particles defy that rule. When one is measured, the other instantly knows how to respond, even if it's halfway across the universe. There's no signal, no force, just correlation that exists without communication. Einstein called this spooky action at a distance, and he didn't mean it as a compliment. He believed the theory had to be incomplete. But Bell's theorem and the experiments that followed proved otherwise. Not only is the spookiness real, but it's built into the fabric of the quantum world. And that brings us to one of the deepest tensions in all of modern science, the conflict between local realism and quantum mechanics. Local realism says that the properties of particles are real and exist independently of measurement, realism, and that information can't travel faster than light, locality. But Bell showed, mathematically and definitively, that no theory respecting both can match the predictions of quantum mechanics. The universe, it turns out, doesn't play by both rules. You must choose. And most physicists have made their choice. They've let go of realism. What does that mean? It means that particles don't have definite states until they are measured. That reality is not a collection of independent facts waiting to be uncovered, but a web of probabilities that solidify only when observed. Niels Bohr embraced this uncertainty. In the Copenhagen interpretation, measurement doesn't just reveal reality, it creates it. Entanglement, then, is not a signal, but a shared destiny. Two particles bound by a common wave function, collapsing together only when we look. But not everyone was content with that answer. The many worlds interpretation, proposed by Hugh Everett in 1957, offered a radical alternative. It says that every possible outcome of a quantum event actually happens in a branching multiverse. When you measure an entangled pair, you don't choose a result. You split the universe. One version of you sees spin up, another spin down. Entanglement, in this view, is a bridge between branching realities, a quiet witness to the splitting of worlds. And then there's the pilot wave theory, or Bohmian mechanics. It restores realism, but at a price. It introduces non-local hidden variables that guide particles through a deterministic landscape, like boats on an invisible quantum current. The pilot wave determines outcomes with certainty, but does so by breaking locality. Again, we are forced to trade one cherished assumption for another. Even stranger are the interpretations rooted in information theory. These suggest that reality itself may be nothing more than information, and entanglement, a correlation between data points in a cosmic simulation. In this view, space-time is emergent, built from entangled bits like pixels forming a digital image. The so-called it-from-qubit hypothesis, explored by physicists like John Preskill and Seth Lloyd, proposes that entanglement isn't just a feature of the universe, it may be the source of it. Which leads to perhaps the most unsettling idea: if reality is information, who or what is doing the computing? Entanglement also puts pressure on our notion of free will. In experiments like the loophole-free Bell tests, the choice of measurement settings must be made independently, free from any correlation with the particle properties. But if the entire system, including the experimenter's choices, is entangled at some hidden level, then true independence may not exist. Are we truly choosing, or just acting out correlations written long ago in the quantum code? These questions are not rhetorical. They touch everything: consciousness, causality, even time itself. Because entanglement seems to ignore time. It doesn't care if particles were once together or always apart. Their connection is not bound by distance or duration, it's timeless, and some researchers are now wondering whether time itself might emerge from entanglement, just as space does. In the Page-Wouters mechanism, time is a property that arises from correlations between entangled systems. There is no global ticking clock, only relationships between quantum states. If that's true, then the arrow of time, the sense of past to future, might be an illusion, a byproduct of decoherence and the unfolding of entangled systems into the classical world we know. And that brings us full circle. Because decoherence, the process by which entangled systems lose their quantum character and become classical, is the key to understanding why we don't see quantum weirdness every day. The entanglement is still there. It's just buried, hidden beneath layers of interaction with the environment. But some believe that if we could isolate systems well enough, maintain their entanglement long enough, we could peer beneath the classical mask and see the true quantum face of reality. For your audience, curious minds raised on Newton and Einstein, this isn't just an intellectual puzzle. It's a spiritual confrontation, a challenge to the idea that the universe is made of things, of objects and causes and effects. Entanglement suggests that it's made instead of relations, that nothing exists in isolation, that the universe is, at its core, a vast tapestry of interwoven possibilities waiting to be observed. And as we step away from metaphysics and return to the frontier of science, we face a new set of challenges. How do we build with this fragile phenomenon? How do we take entanglement from the vacuum of theory and anchor it in the rough soil of engineering? In the next part of our journey, we'll explore those very questions. How scientists are working to overcome the practical limitations of entanglement and where the road may lead next. It's one thing to observe entanglement in a clean, sealed chamber under tightly controlled lab conditions. It's another to harness it, to take this fragile, almost mythical force and make it stable, scalable, and useful. Because while entanglement may be one of nature's most powerful phenomena, it's also one of the most difficult to work with. It resists control, it recoils from interference, it shatters at the slightest touch of heat, light, or time. And yet scientists are learning to shape it, slowly, carefully, atom by atom, photon by photon. The first major challenge is decoherence, the tendency of entangled systems to unravel when exposed to their environment. It doesn't take much. A vibration, a stray electron, even a glimmer of background radiation can break the delicate correlations between entangled particles. In practical terms, this means that entangled qubits in a quantum computer or photons in a quantum network must be isolated with extreme precision. This is why so many of today's quantum machines operate near absolute zero or inside magnetic vacuum chambers. They're not being dramatic, they're just trying to keep the entanglement alive. But isolation alone isn't enough. You also have to scale. A single pair of entangled particles is impressive. A dozen is extraordinary. But if we want to build practical quantum computers or global quantum networks, we need thousands, maybe millions, of entangled qubits operating in concert, staying coherent long enough to complete useful tasks. This is where quantum error correction comes in. Unlike classical bits, quantum information can't be copied or backed up in the traditional sense. Instead, error correction works by entangling the data across multiple qubits in such a way that if one qubit experiences a disturbance, the system as a whole can detect and correct it without ever directly measuring or collapsing the quantum state. It's a kind of digital immune system for entanglement, and it's essential for anything more advanced than a proof of concept. But even error correction has limits, especially when scaling to larger systems. That's led researchers to experiment with entirely new materials and architectures for quantum devices. Some teams are using topological qubits, quasi-particles that store quantum information in the shape of their collective fields rather than the state of individual particles. These systems are more resistant to noise and may hold entanglement longer, acting like quantum knots that don't easily come undone. Others are pursuing entanglement via trapped ions, photonic circuits, or neutral atoms suspended in light fields. Each approach has trade-offs: speed, stability, scalability, but all share the same goal: taming entanglement just enough to build with it. Then there's the challenge of distribution. Creating entanglement in a lab is one thing. Sharing it across a city, a continent, or between satellites and ground stations is another. Quantum communication requires entangled particles to be transmitted, typically via fiber optics or free space lasers, and every kilometer introduces loss. Photons are absorbed, scattered, or decohere along the way. To overcome this, researchers are developing quantum repeaters, devices that restore or regenerate entanglement without violating the no-cloning principle. These repeaters act like pit stops in a long-distance race, briefly storing entanglement and relaying it onward using entangled links. The dream is a global quantum internet where entanglement is not just created and measured, but delivered on demand anywhere in the world. In 2025, a joint effort between European and Japanese teams succeeded in entangling quantum nodes 600 kilometers apart using a combination of ground-based fiber and satellite relays. The key innovation was entanglement swapping, a process where two previously unentangled systems become entangled by interacting with parts of another entangled pair. This ability to relay entanglement through intermediary nodes is critical to scaling up any future quantum network. Meanwhile, challenges persist in integration. Quantum systems don't play well with the classical world. Classical electronics run hot, fast, and loud. Quantum devices run cold, slow, and quiet. Getting them to communicate is like having an opera singer duet with a jackhammer. But engineers are finding ways to bridge the gap, developing hybrid interfaces that convert quantum signals into classical ones and back again without losing the entangled states in the process. And hovering over all of this is the question of control. Entanglement isn't just delicate, it's deeply unintuitive. You can't simply point a laser and entangle that. It requires precise alignment, phase matching, and often sheer statistical patience. Even with today's most advanced labs, creating consistent high-fidelity entanglement is an art as much as a science. Still, progress is being made. In 2025, researchers at Caltech unveiled a chip-scale quantum processor capable of generating and maintaining entanglement across 50 qubits for over 200 microseconds, an eternity by quantum standards. It's not ready for commercial use, but it's a signpost, a hint of what's coming. And what is coming is extraordinary. Imagine networks of quantum sensors blanketing the planet, detecting earthquakes before they strike, or scanning for underground water reserves with unprecedented accuracy. Imagine satellites exchanging entangled signals across oceans, creating communication channels that are physically unhackable. Imagine quantum computers solving chemistry problems too complex for the human mind, discovering new medicines, materials, or energy sources not in years but in minutes. All of it begins with solving these challenges, with taking entanglement from the strange and theoretical and making it stable, practical, and routine. We're not there yet, but we are closer than ever. Of course, every breakthrough also opens the door to new mysteries. As we begin to engineer entanglement at scale, some physicists are asking, are we creating these states, or uncovering something that was always there? Could entanglement be a fundamental structure of the universe, not just between particles, but between everything? In the next segment of our journey, we'll explore the bleeding edge of that question, where entanglement meets quantum gravity, black holes, and the very nature of space and time. For over a century, physicists have lived with a schism. On one side, general relativity, a grand, elegant theory that treats gravity as the curvature of space-time. On the other, quantum mechanics, a chaotic probabilistic world of particles and uncertainty. Both are wildly successful. Both predict real phenomena with astonishing accuracy. But they don't speak the same language. They don't even agree on what space or time is. This tension has haunted physics for decades, but in recent years, a new voice has emerged, one that speaks both dialects, quietly translating between them, and that voice is entanglement. In 2025, a growing number of researchers began to suggest something radical, that space-time itself may be emergent, not fundamental, not a backdrop, but something that comes from quantum entanglement, stitched together, moment by moment, from correlations between quantum systems. This idea isn't science fiction. It's rooted in serious theoretical work, beginning with the holographic principle and culminating in models like ADS-CFT duality. In these models, a universe with gravity in a curved space, like anti-de Sitter space, can be described by a quantum field theory without gravity on the boundary of that space. It's as if a lower dimensional quantum system encodes all the information in a higher dimensional reality, and at the heart of this encoding, what binds it all together, is entanglement. The proposal, put forward most famously by Juan Maldacena and later built upon by Mark van Ramsdonk and others, is that entanglement constructs space-time. Remove entanglement between two quantum regions and their space-time connectivity fades. Maintain it, and the geometry holds. It's a wild idea that wormholes, black hole interiors, even time itself may be byproducts of entanglement between distant quantum degrees of freedom. A vivid example of this comes from the ER equals EPR conjecture, proposed by Leonard Susskind and Maldacena. It suggests that Einstein-Rosen bridges, wormholes, are actually just entangled pairs of black holes. In other words, that a wormhole is entanglement made geometric. Two black holes entangled at a quantum level might be linked by a non-traversable bridge through space-time, invisible to classical observation but implied by quantum correlation. This blurs the line between information and geometry. If true, it would mean that the shape of the universe, its very topology, is governed not by mass and energy alone, but by how quantum systems are entangled with one another. And this leads to another profound idea, that gravity itself may be an emergent force, that it's not fundamental, like a particle or field, but the statistical behavior of quantum information trying to maintain its correlations across a vast system. Like pressure emerging from molecules or temperature from motion, gravity might emerge from entanglement, trying to stay coherent as the universe evolves. Supporting this are recent insights from tensor networks, mathematical models that describe entanglement structures using geometrical webs. These networks naturally give rise to curved spaces. In simulations, when entanglement between nodes is increased, the resulting geometry curves inward, mimicking gravity. The more entanglement, the more connected space becomes. The less, the more fragmented. In 2025, physicists at the University of Geneva used such models to simulate an expanding space-time driven purely by changes in entanglement entropy. They found that the growth of entanglement across quantum fields mirrored the evolution of a universe in time, suggesting that time itself may be a side effect of entanglement spreading. And that raises a terrifying, beautiful possibility that if entanglement is space-time, then the breakdown of entanglement could be the breakdown of reality. That in a sense, the fabric of the cosmos is not woven from strings or particles, but from shared information, from entangled threads pulling and knotting together across the vacuum. This has implications for black holes too, long the ultimate testing ground for theories of gravity and quantum mechanics. In the 1970s, Stephen Hawking showed that black holes emit radiation and eventually evaporate, leading to the so-called information paradox. If a black hole disappears, what happens to the information that fell into it? Entanglement may provide the answer. In newer models, the information doesn't vanish. It becomes encoded in the Hawking radiation itself, entangled with the interior in such a way that eventually all the information leaks out, but scrambled beyond recognition. Recent work involving quantum extremal surfaces and the island formula suggests that entanglement entropy between a black hole and its radiation follows a predictable curve, a sign that information is preserved if bizarrely transformed. So we are left with a view of reality that is more fragile, more interconnected, and more dependent on quantum information than ever imagined. Space is not a stage, it's a consequence. Time is not a flow, it's a byproduct. The cosmos doesn't just exist, it entangles. And yet, we still lack a full theory of quantum gravity. We don't know how to unify general relativity and quantum field theory into one coherent framework. But entanglement, once thought of as a weird side effect of quantum mechanics, may be the bridge we've needed all along. The implications ripple outward. If space-time emerges from entanglement, then perhaps consciousness does too. Perhaps the act of observation, which collapses wave functions and creates entangled outcomes, is not just a passive act, but a participatory one. A way in which mind and universe are linked through shared information. It's a tantalizing idea that behind the curtain of particles and forces, of fields and waves, lies something deeper. Not a thing, but a relationship. Not matter, but memory. a web of correlations that binds all things, not in space, but as space. Entanglement isn't just real, it might be the most real thing in the universe. If entanglement can shape space-time, bend information, and underpin black holes, then surely it belongs only to the cold, vast reaches of physics. But what if it's closer than that? What if entanglement doesn't just exist in vacuum chambers or particle colliders, but inside us? In the chemistry of our cells, the reactions in our brains, and perhaps even the origin of life itself. In recent decades, a bold and rapidly growing field has emerged: quantum biology. Its premise is simple but revolutionary, that quantum effects, especially entanglement, may play an essential role in biological processes. Long thought too delicate to survive the warm and wet chaos of living systems, entanglement may in fact be resilient enough and useful enough to persist and guide molecular functions. Start with enzymes. These biological catalysts make life possible by speeding up chemical reactions a trillion-fold. Classical biochemistry explains much of their behavior, but not all. Some enzymes enable reactions that by classical logic shouldn't happen at all. They move particles, protons or electrons, across barriers without enough energy. And the proposed mechanism? Quantum tunneling, a phenomenon underpinned by the same wave function structure that gives rise to entanglement. But tunneling alone isn't the whole story. In 2022, researchers at Oxford proposed that entangled vibrational states within enzymes may allow precise control over the geometry of chemical bonds, essentially using quantum correlations to orchestrate reactions more efficiently than random thermal energy ever could. The enzyme doesn't just jiggle the molecules, it knows in a strange and silent way when and where to act. The case becomes stronger with photosynthesis. Plants and bacteria convert light into energy with near-perfect efficiency. How? Experiments using ultrafast laser pulses have revealed that when photons strike pigment protein complexes, the resulting energy doesn't simply wander randomly, it travels through multiple paths simultaneously as a quantum superposition. And within those pathways, researchers have found evidence of entanglement, fleeting but measurable, guiding the energy toward the reaction center with laser-like precision. This isn't speculation. In 2020, entangled photon spectroscopy was used to directly probe these systems, revealing that the pigment molecules maintain quantum correlations longer than anyone expected, even at physiological temperatures. It's as if evolution stumbled upon a quantum algorithm, designed not in silicon, but in chlorophyll. And then there's olfaction, our sense of smell. The prevailing theory for decades was shape-based. Molecules bind to receptors that recognize their geometry, like keys in locks. But this model struggles to explain how we distinguish between molecules with nearly identical shapes, but wildly different odors. An alternative theory, first proposed by Luca Turin, suggests that our noses may detect molecular vibrations through quantum tunneling, allowing them to distinguish molecules by how electrons leap across them. Some researchers now believe that entanglement between molecular states might enhance this effect, turning smell into a quantum mechanical resonance, more akin to hearing than touch. Still, the most provocative claims emerge in the realm of genetics. DNA replication, protein folding, and even gene expression involve processes so exquisitely precise and yet so vulnerable to noise that some scientists have proposed quantum coherence as a stabilizing influence. In 2025, researchers at MIT detected quantum entanglement signatures in simulations of DNA base pair reading, suggesting that quantum correlations may help prevent transcription errors during cellular replication. Could this extend to the emergence of life itself? Some theories of abiogenesis, the origin of life, now posit that early Earth conditions may have enabled entangled molecular systems to form spontaneously, creating the kind of robust, self-organizing structures necessary for prebiotic chemistry. In this view, entanglement wasn't a side effect of life, it was the ignition, a way for non-living molecules to correlate behaviors across space and time, increasing their functional complexity and stability. One bold hypothesis by physicist Jim Al-Khalili and biologist John Joe McFadden proposes that evolution itself may have quantum roots, that mutations in DNA, typically considered random, might sometimes follow coherent pathways enabled by quantum processes. This doesn't imply a conscious hand, but a kind of hidden structure behind chance, where entanglement shapes the landscape of possibility. And then, inevitably, the question of consciousness arises. It's one of the oldest mysteries. How do electrical signals and chemical gradients in the brain give rise to subjective experience? Some researchers believe the answer might lie in quantum entanglement. The Penrose-Hameroff-Orch-OR theory posits that consciousness arises from quantum events inside microtubules, structural components of neurons, that may host entangled states capable of sustaining coherence over surprising timescales. Though controversial, this idea gained traction after 2023 experiments at the Max Planck Institute showed evidence of entangled spin states in cytoskeletal proteins, hinting that biological systems can preserve quantum information under the right conditions. If true, it may explain how disparate brain regions synchronize with uncanny speed, or how memory, attention, and awareness can arise from physically dispersed networks of cells. Still, caution is warranted. The brain is noisy, warm, chaotic. The idea that delicate quantum states could persist long enough to influence cognition remains hotly debated. Yet the boundary between impossible and merely unproven is one physics is constantly redrawing. For now, we are left with tantalizing hints. Entanglement is no longer confined to the abstract or the cosmological. It might live in the green of leaves, the breath of cells, the structure of smell, even perhaps in the quiet unity behind conscious thought. And if that's true, then we must reconsider where entanglement ends and where we begin. In the next part of our journey, we'll turn toward what lies ahead, the new experiments, the unsolved puzzles, and the technological revolutions entanglement still has yet to spark. As the lights dim on the proven and the polished, we turn our gaze toward the unknown, the flickering frontiers where entanglement is still more question than answer. We've learned that entanglement exists, we've learned how to manipulate it in labs, and we've even begun building machines with it. But if the history of science has taught us anything, it's that for every mystery solved, a dozen more open in its place. The first challenge is scalability. Yes, we can entangle particles, pairs, sometimes small clusters, but to create systems with hundreds or thousands of entangled components, that remains an enormous leap. A truly scalable quantum computer, for example, will require sustained entanglement across hundreds of error-corrected qubits, with coherence times long enough to execute meaningful computations. No current platform, trapped ions, superconducting circuits, photonic lattices, has fully cracked the code. Some believe the answer lies in modular systems, building small entangled processors that can then be linked together via photonic entanglement. Much like classical computers use local networks to create larger ones. Others propose topological qubits, exotic quasi-particles, whose entangled states are more robust because they're encoded in the geometry of space itself rather than a physical property of matter. In either case, the dream is clear: to move from fragile proof of concepts to industrial strength entanglement, scalable, stable, and fast. Another looming question is interpretability. Even as we manipulate entanglement with growing skill, we still don't fully understand what it means. Is it a physical connection? A shared wave function? A statistical trick? When two particles are entangled, what exactly is connecting them? Are they part of the same thing, just split in space? Or are we misreading the phenomenon entirely, projecting locality onto something inherently non-local? This becomes critical when entanglement touches foundational physics, like quantum gravity. If space-time itself emerges from entangled states, then we need a rigorous theory explaining how geometry arises from information. Right now, several candidate models exist, but none are complete. We have hints, tensor networks that resemble curved space, entanglement entropy equations that mimic Einstein's field equations. But no unified framework yet ties these threads together. Then there's the challenge of time. In classical physics, time is a parameter. In quantum mechanics, it's strangely absent, an external clock rather than an internal variable. But in quantum gravity, time may emerge from entanglement between systems. Could the arrow of time, our perception of before and after, be nothing more than entropic flow between entangled regions? Some researchers are designing experiments to test this, creating closed quantum systems and monitoring how their internal correlations evolve. If entanglement truly defines temporal structure, the implications for cosmology and philosophy are staggering. More immediately, there's the issue of integration. Right now, quantum technologies are siloed. Quantum computers in one lab, quantum sensors in another, communication protocols tested on satellites but not yet merged into a unified system. The next decade will likely see efforts to build quantum ecosystems, where entanglement flows seamlessly between modules. A quantum computer might use entangled sensors for environmental input. A quantum satellite might share data with a terrestrial processor via entangled photons. The pieces are being built, now they must connect. And yet, even with these challenges, the potential of entanglement continues to expand, often in directions no one predicted. In 2026, researchers at a university in Singapore reported preliminary success in entangling mechanical systems, tiny vibrating membranes that maintained coherence over tens of milliseconds. These systems could eventually serve as quantum transducers, bridging optical photons which travel well with microwave qubits which compute well. The more entangled media we master, the more flexible our architectures become. There's also momentum building around entanglement harvesting, extracting entangled pairs from the vacuum itself. In quantum field theory, the vacuum isn't empty. It seethes with fluctuations, virtual particles popping in and out of existence. Some theorists suggest that by placing detectors in certain configurations, one can harvest the naturally occurring entanglement of the quantum vacuum without destroying it. It's a bizarre notion, but if true, it could lead to entirely new forms of quantum energy, sensing, or even propulsion. In the realm of cosmology, scientists are beginning to wonder whether the cosmic microwave background, the oldest light in the universe, carries a hidden fingerprint of primordial entanglement. If so, it would offer a direct link between quantum phenomena and the birth of the universe. It could mean the Big Bang wasn't just an explosion of matter and energy, but of correlations, entanglement woven into the universe at its inception. And what of macroscopic entanglement? Could we entangle objects visible to the naked eye? Could we one day entangle a clock and a mirror, a bacterium and a crystal? Recent advances in optomechanics and cavity quantum electrodynamics suggest that we're not far from the day when entanglement reaches into the everyday world, blurring at last the boundary between the quantum and the classical. Yet with every advance comes a whisper of caution. Entanglement is not merely a tool, it's a message. A clue from nature that our intuition about separation, about locality, about what it means to exist as an independent entity, may be wrong. Entanglement invites us to rethink causality, identity, and the very definition of a system. It reveals a universe not made of parts, but of relationships. And as we move forward, building quantum computers, secure networks, and entangled sensors, we must ask, are we unlocking nature's secrets or building mirrors to reflect our own limitations back at us? In the final chapters of this journey, we'll reflect on what this all means, not just scientifically, but existentially. What does it say about our place in the universe if the most fundamental truths are not about things, but about how things relate? We often imagine the universe as a great machine, a vast clockwork, ticking forward in silence, indifferent to our existence. But quantum entanglement tells a different story, one that's less about isolated parts and more about interwoven threads, more tapestry than machine, more song than structure. At its heart, entanglement whispers something revolutionary, that nothing exists alone. The spin of an electron, the path of a photon, the chemical reaction that fires in a synapse, they are all in some way shaped by their connections to the rest of the universe. This isn't poetry. It's measurable. It's been tested again and again in the lab. And it suggests that what we call reality might be less about discrete objects and more about the invisible relationships between them. This idea reaches far beyond physics. It touches the core of how we think about existence. In classical science, to know something was to isolate it, to reduce it to its smallest parts, hold them still, and study their behavior. But in the quantum world, that very act of isolation changes the system. Observation collapses possibility, measurement rewrites the state. And in entangled systems, this collapse happens not just locally, but everywhere the system stretches. Your act of looking here can change what's true over there. This isn't just strange, it's humbling. It means the observer is not separate from the observed. It means our questions shape the answers we receive. That in a deep and mysterious way, we participate in the reality we're trying to understand. And this forces us to ask, what else have we misunderstood by looking too narrowly? Take identity. In a world of entanglement, the idea of a self-contained object becomes fuzzy. Even the notion of a thing starts to erode. What is an electron if not its interactions? What is a person if not their relationships? This is not mysticism, it's a scientific consequence of entangled systems. The properties of the whole are not reducible to the properties of the parts. And this is perhaps the most profound lesson of all, that the universe is contextual. Things don't just exist, they exist in relation. This perspective is ancient in some cultures. Eastern philosophies have long described the world as interdependent, where the self is not a boundary, but a node in a network. Indigenous worldviews speak of kinship between land, animals, and people, not as metaphor, but as fact. And now, in the equations of quantum theory, we are beginning to see science echo those truths, not because of ideology, but because the data demands it. Entanglement challenges not just physics textbooks, but our assumptions about separateness, causality, and control. It humbles the human tendency to draw lines between categories, subject and object, cause and effect, mind and matter. Because if particles can be connected across light years, if choices made here can influence outcomes there, if time itself is shaped by how systems share information, then maybe we need to rethink what we mean by reality. Some have even wondered if consciousness itself is an emergent property of entangled systems, not consciousness as in thought or self-awareness, but as presence, as the capacity of a system to be in relation to others. Perhaps the mystery of why is there something rather than nothing is actually, why is there togetherness rather than aloneness? And perhaps the answer lies in entanglement's refusal to let the universe be pulled apart. This is not to say we abandon precision or replace physics with philosophy. On the contrary, quantum mechanics is one of the most precisely tested theories in all of science. But in entanglement, it reveals a second gift, not just control, but perspective, a deeper way of seeing. We are no longer bystanders, we are participants. When we speak of a quantum future, quantum computers, quantum communication, quantum sensors, we are also speaking of a future where interconnection is not just a technological feature, but a conceptual one. A future where science invites us to see ourselves not as rulers of a clockwork cosmos, but as threads in a pattern too vast to measure. And perhaps that's the final revolution entanglement offers, not in tools or theories, but in imagination. It offers a chance to reimagine ourselves as part of a whole we can never fully see, but to which we are always connected. If you've made it this far, you already know something many don't. Quantum entanglement is not just an obscure physical principle. It is not some footnote in the story of modern science. It's a thread, delicate but unbreakable, that weaves through nearly every layer of the universe. It connects not only particles but disciplines, perspectives, even people. And now, here at the edge of that thread, we find ourselves asking a question not often found in physics journals. What does all of this mean? It's one thing to learn that entanglement is real, that it's measurable, that experiments have confirmed its predictions again and again, that we've used it to build the early scaffolding of a quantum internet, that it's enabled teleportation of information across fiber optics, and maybe, one day, across space itself. But it's another thing entirely to ask, what kind of reality allows this to happen? We've seen that entangled particles don't behave like separate objects. They behave as if they are parts of a single, indivisible whole, regardless of the distance between them. And while our mathematics can describe this phenomenon with startling accuracy, the deeper meaning of this unity eludes us. We're left peering through a glass darkly, glimpsing only fragments of a truth too vast to hold. Perhaps the most startling realization is that entanglement doesn't just reveal how the universe works. It reveals how we think about it. It exposes the limitations of the classical mind. A mind trained to divide, to categorize, to look at the world through the lens of separation, subject and object, self and other, here and there, now and then. Entanglement tells us these boundaries are conveniences, not truths. It's tempting to think of the quantum world as weird, as if it were somehow less real than the everyday world we experience. But perhaps it's the other way around. Perhaps the quantum world is the real world, and the one we navigate daily is merely a softened, averaged-out approximation, safe for human minds, built for survival, but blind to the deeper code. Entanglement may be our first clear glimpse into that code, a peek behind the veil. There's also something poetic in the timing. In an era where the world feels increasingly fragmented, politically, socially, environmentally, entanglement reminds us that connection is not only possible, but natural. That independence, while empowering, is not absolute. That even in a universe hurtling toward entropy, there remain systems that choose coherence, that bind together instead of breaking apart. There is a kind of quiet courage in that idea. Because entanglement isn't easy, it's fragile, it requires perfect conditions to arise and immense care to sustain. And yet it endures. From photons born in the heart of a star to ions suspended in laboratory vacuums, it defies distance, it laughs at isolation, it insists on togetherness. For some, this notion brings discomfort. It challenges the cherished idea of control, of individuality, of a clean boundary between observer and observed. But for others, it brings comfort. A sense that the cosmos is less a machine and more a web, a network of relations, all humming in quiet synchrony. And what, after all, are we? A collection of atoms? A brief pattern in a sea of entropy? Or are we something more, something made real by the sum of our connections? In entanglement, we find a metaphor as much as a mechanism. It invites us to look differently at everything, not as isolated phenomena, but as points in a field of influence, echoes in a shared vibration. It tells us that to observe is to participate, that to know is in some sense to join with, and this does not diminish us, it deepens us. It doesn't mean we're less real, it means reality is more than we thought. And so, as this chapter draws toward its end, we return to the question that began it all. Are particles even real? After all we've seen, the double-slit paradoxes, the collapsing wave functions, the invisible threads of entanglement, the answer may be both yes and no, or neither, or something else entirely. Maybe the better question is reality even made of particles at all? Or is it made of relationships, fields of potential, stitched together by entanglement, revealed only in moments of interaction? Whatever the answer, one thing seems clear. Entanglement is not a trick of measurement. It is not a glitch in the matrix. It is the matrix. It is the hidden symmetry behind everything we see. There's a moment, when staring too long into the strange heart of quantum mechanics, that you begin to feel the edges of language bend. You start to realize that maybe we've been asking the wrong questions, that real might not mean what we thought it did, that maybe, just maybe, the universe doesn't care about our categories, particles, waves, fields, time. It only cares about relationship. Entanglement is not a theory anymore, it is a fact. It's been tested, confirmed, broken apart and reassembled. We've sent entangled photons into space. We've used them to encrypt messages, to teleport states across labs, to make clocks tick more precisely than ever before. And yet, for all our mastery, we still can't say why the world allows such a thing. Why should two particles, light years apart, share a fate? Why should observation here affect measurement there? Why should the universe, which from the outside appears vast and silent and cold, contain a rule that so deeply, so fundamentally binds? Perhaps because it's not a rule at all. Perhaps it's a signature, a watermark, a clue that the universe isn't made of objects, but of meaning. Not things, but interactions. Not matter, but memory. Think about what we've seen. From the entangled spin of electrons to the teleportation of quantum states, from the eerie violations of Bell's inequalities to the idea that space-time itself may be woven from entanglement, from the humming interior of chloroplasts to the neural whispers of the human brain, entanglement keeps showing up, not as anomaly, but as architecture. It doesn't hide, it structures, it informs. The deeper we look, the more entanglement becomes not a feature of reality, but its foundation. Beneath every measurement, behind every equation, there lies a quiet truth. Nothing exists in isolation. Even the void between stars may hum with unseen bonds. And maybe, so do we. We are, after all, quantum systems. We are made of the same fields, obey the same laws, spin in the same uncertainties. If entanglement is the language of the universe, then somewhere, somehow, we too are written in it. Not just our atoms, but our attention, our choices, our perceptions. Every act of seeing changes what is seen. Every act of knowing leaves a trace, and every trace carries with it a web of echoes that stretch beyond comprehension. This doesn't make us magical, it makes us belong. You, sitting there watching this, are not separate from the things you study. You are part of the experiment, entangled with the world not just biologically or chemically, but informationally. You are not an outsider looking in. You are the universe, briefly observing itself. This may sound poetic, but it is science, the kind of science that doesn't just answer, but awakens. The kind that reminds us that curiosity is more than entertainment. It is participation. Entanglement doesn't just connect particles, it connects questions, it connects minds. And so, as we close this journey, perhaps the most profound realization isn't what entanglement reveals about photons or atoms or space, but what it reveals about us. That reality is not built from the solitary, but from the shared. That to understand anything we must listen to everything, that even in a universe governed by entropy, there is still a force that binds, that coheres, that refuses to come undone. And that force is entanglement. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.